of talked about this, but let's dive into it a little bit more around these flow rates. What are the expected flow rates of fixtures in your home? I just did a quick Google search online to pull out what some of the common expected flow rates were for common household fixtures. And this is one table that I was easily able to find, and I'm gonna compare that to the common fixtures flow rates that we brought up earlier in the lesson for households.
So this is
Mm-hmm.
quite quite an interesting table. We're talking about the first one, your
Mm-hmm.
Google common fixtures. I'm quite challenged by that table, but I've I've seen this type of overestimation often in the literature.
The numbers are
Uh,
much bigger than the ones provided in yours
yeah,
below, right? That's the big thing to point out.
yeah, and that's many of these advices come from the utility industry, water utility industry, um, and we've spent a lot of time in Australia sorting out what really goes on in a house with the appliances. We need to be a little careful though, because appliances are somewhat different in North America, but not totally different. For instance, you use a lot more water in your toilets, but that's changing rapidly.
Mm-hmm.
Um, However, the volume of water used in your toilet really doesn't change the flow rate much, does it? Because it's just being supplied by
It's
a
a trickle
system.
top up. Yeah.
Yeah. So that, where are we?
The
You
toilet
know,
on this one, they call it the water closet with gravity tank. They're suggesting that the flow rate is 2.5 gallons per minute or 10 liters per minute, right? And take that compared to you've got half as much, 5 liters per minute toilet and 1.3 gallons per minute toilet. Yeah.
yeah. So just be aware of that. There are lots of tables all around the place that state these flow rates for different sorts of fixtures, and they're usually always gross overestimations. For instance, the shower head here, it's got 19 liters a second, so that's 19 liters a minute. Sorry, that's an elephant washer. That's not a normal shower rose, but
Oh, yeah.
some people
Imagine.
like to have a rainwater a rainwater downpour type shower.
Right.
Um, Water efficiency in our country has driven down showers to less than 9 liters a minute,
Mm-hmm.
and the modern water efficient showers that you don't have to run around under to get wet are about 7 liters per minute. You can see
Mm-hmm.
there's a really big difference there. Um,
So that's the first point is that you'll see quite large overestimates on these individual fixtures. And isn't the second issue that where there's estimates about how many fixtures might be open at any one given time, right? In terms of how big you might have to size your pump. Um, I did read some stuff online as I was just preparing for this lesson around ways to estimate how many fixtures might be open at the same time, but still quite conservative. Really, actually, quite conservative.
yeah, and um, so if you have as we talked about before, if you have a low flow washing machine, a water efficient washing machine,
Mm-hmm.
and the saturation of those is fairly strong throughout the world now, in countries like North America and Australia and the United Kingdom, um, the machine itself is expecting 4 liters a minute or less of flow rate. Any higher flow rate going to that machine is being buffered by the pressure reducing valves in the machine,
Mm-hmm.
and a lot of people don't realise that. Um, so in our Australian guide, we've got the washing machine less than 12 litres a minute. Um, the only time where the washing machine actually probably needs any sort of pressure is, say, in the rinse cycle, the spray rinse cycle that some of them have. Ours does. Our very low uh, water using washing machine actually has its own internal pump to produce the rinse cycle.
Hmm.
So you need to look closely at how things work now.
So it's worth opening up your manufacturer's pamphlet sometimes, possibly, to look at what your appliances actually use and what kind of flow rates they require. And is would that information be available in the manufacturer's pamphlet
Uh,
necessarily?
oh, they are, and this is
Mm-hmm.
really good advice, Michelle.
Mm-hmm.
Really serious designers usually have their own homes. When they're specifying the appliances they want in their homes, and if they're going to do a sustainable energy or sustainable water strategy, and I hope you do both, is they're actually getting the specifications for the appliances to not only work out how they perform, but to make their choices about the appliances. And we did in our renovation of our city home 3 years ago. So we not only wanted the appliances to be functional and look good and do what we wanted them to do, we got down and dirty with their energy and water use
Mm-hmm.
because we're off grid for energy and water. So we wanted to know how these appliances really work, and that's what I'd recommend. So we're a long way away from pumps, but this is directly related to pumps.
Mm-hmm. And
So,
and then when you have your flow rates for your fixtures, how many is reasonable to assume will be operating simultaneously? Is that also a per household consideration where you look around and I mean you could manage that with behavior to some
yeah,
extent.
this it's a really good point you make, Michelle. This really irks me where conservative designers say just assume everything's on at once. But you can easily manage that with behavior, as you correctly pointed out. And behavior is very easy to manage. It's not such an inconvenience to say, um, we don't
Don't
need to have
shower
it.
don't shower the washing machine is on, just wait, you know?
Yeah, we used to do that in our country home.
Mhm.
So we had a very small pump and we weren't
Mhm.
really that inconvenienced. Or if you've got many showers throughout your house, you don't need to turn them all on at once. And it's probably unlikely that you will.
Mhm.
And if your house has many bathrooms, and um, we've been watching these design programs from North America, and there seems to be a lot of bathrooms in North American houses. Just because there's 4 bathrooms, it doesn't mean that 4 showers and 4 toilets are all operating at the one time. So you've got a little note here, Michelle, that assuming that 2 appliances could be operating at the one time, and that's what I would do. And if you've gone to the trouble to have an energy efficient and water efficient house that has rainwater harvesting, you would certainly be going to the small trouble of sorting out your behavior so you're not over designing your devices.
Mhm.
Um, so, but we need to think this through too. A toilet is a slow top up. Um, Even the 5 litres per minute, we've got monitoring of how households work, and we've got monitoring of thousands of households. The average flow rate going into toilet systems is less than 1 litre a minute, um, because they top up very slowly, because there's actually a valve inside toilet systems that are fully open when they're empty, but as this toilet system fills up, it closes and the flow rate
Mhm.
changes and reduces all the way until zero.
Mhm.
So at the very first top up of your toilet, it might be the maximum flow rate, whatever you can supply. But your toilet cistern valve actually stops that flow rate very quickly as it fills up. So the flow rate diminishes as your cistern fills up. So the average topping up for toilets was around 1 litre per minute and
Hmm.
probably less. So if you add that to, say you've got a shower on and you've got a water efficient shower, say 9 litres a minute. So you're talking about 10 litres a minute you're needing to get if you've got the shower and the toilet. Your washing machine is, if you've got a water efficient washing machine and the shower on at the same time, um, you're we're really hoping for it's going to be a lot less than 12 litres a minute, but say that it is, and the shower you're talking around about 20 litres a minute. So most of your garden variety small pumps will supply about 30 litres a minute. I think
Right.
it,
So these are small numbers, really, in the world of pumps. These are not big volumes.
they're baby numbers, Michelle.
Mm-hmm.
So,
Mm-hmm.
um, and the pump pressure, the smallest pumps around, and they're not the smallest, but the most commonly used in the rainwater industry has been around the 300 to 350 kPAs. Um, that's a external pump. If it's in the bottom of a rainwater tank, it'll be higher. And it's going to be providing about 30 metres of head, which is about 100 feet.
Mm-hmm.
Um,
Pressure.
and, and they're usually quite adequate unless you're lifting water up many stories in a house, or you've got
Mm-hmm.
something different about your supply situation.
Well, what if you have? I mean, we didn't talk about any additional losses that you might have in your system. For instance, I don't know if it'd be significant, but if you had long pipe runs, or if you had end of line treatment, for instance, like a UV that had a significant pressure drop across it. Those are the kind of things you might think about.
or a
Additional pressure
very
losses.
or a very fine filter, which will create substantial pressure drop as well. That's why if
Mm-hmm.
you're going to put a very fine filter, you don't put it at the pump, you put it at the end use where you really need it. So my own our house, we've actually got the zero point 0.1 micron filter only on the drinking water tap,
Mm-hmm.
because there's no point pumping water through that filter for the whole house. It's just not needed. So
So, do you find your drinking water tap, has a lower pressure, it comes out a little bit slower than maybe your hand basins where you're washing your hands?
yeah, it
Um,
does.
mm-hmm.
So you have that pressure and flow rate loss because the pump's trying to push water through that filter. Um, so also something to watch out for when we first set up our city rainwater harvesting system well over 20 years ago. We had this crazy plumber who put lots of bends in the lines, and you know, and in fact he was crazy about bends, I think. So if you've got lots of bends in your line and you've got long delivery lines, there'll be losses in pressure and flow rate supplying your house.
Mm-hmm.
Um, to give you an idea, when I when we renovated the house, we actually renovated the plumbing system, um, and we halved the length of um, transfer by making the plumbing direct to the appliances rather than around the world, and we eliminated almost all bends in the system. There's only about 2 or 3 bends in the system, whereas before the plumber had about 50 bends. Don't ask, I don't know why he did it. And we immediately noticed that we have a more even and higher pressure flow rate, and the pumps worked, uh, you know, far less harder than, is that the right way to put it?
Mm-hmm.
The pumps used a lot less energy, and you could tell they were not working as hard now that the the supply lines were short and there were not many bends.
Mm-hmm. So I mean, if if one of our students is going to go out and try and select the right pump, I mean, do they actually need to count all the different bends and all the length of pipe and all of the different devices that might cause pressure loss and have those numbers figured out to add them up and then look on a pump curve, or is there some general rules of thumbs in a standard house that they can use when they're looking at sizing their pump?
The general rule I'd use is, um, just in a normal house situation, just work to minimise the number of bends and the length of supply to each of the end users. You know, washing machine, toilet, whatever you're using it for, garden,
Mm-hmm.
and and that will minimise your losses, which is easier than trying to do the infernal arithmetic of the losses at every bend and
Mm-hmm.
length in your system.
Mm-hmm.
Um, and that's probably a good rule of thumb. Um, there'll always be some loss of pressure and flow rate from what your pump will supply versus what you'll end up in the tap. So there'll be a friction loss in the pipes. The other thing we do is there was a standard in Australia which we ignore now that said rainwater supply lines need to be smaller than mains water supply lines in the house. What that ended up doing is maximizing friction head loss. So the rainwater supply lines were 15 millimeters and the mains water supply lines were say 25 millimeters, just for argument's sake. We've replaced all those and in my own house and others that we've advised with 32 millimeters, which is over an inch for you guys, lines, and that actually completely eliminated the majority of the friction head losses in the supply.
House. So the supply, I'm curious. You said the size of the typical supply piping, the typical plumbing supply piping in Australian homes is how big? Did you say?
It's probably around 20 millimeters. And the rainwater supply plumbing was quite a bit less than that in one of the crazy standards or guidelines that were put out.
I'm scratching my head, Peter, because wouldn't that mean that you'd have two set of supply lines if you had separate rainwater supply and is that basically implying that you should have two separate plumbing systems in your house? One to supply rainwater to your tap and one to supply mains water to your tap. That's kind of what I'm picturing when you're saying the rainwater supply system.
Well spotted, Michelle. The plumbing code was created by the water utilities who weren't keen on rainwater harvesting, and it was forcing two different systems, so that's no longer applies, and you have the same system.
Yeah, I'm kind of picturing, in all honesty, there's going to be a lot more retrofit here, where folks are now seeing rainwater harvesting as a really great supplemental supply system, and you're going to be tying in this rainwater harvesting system to the existing plumbing in your home, right? And hopefully changing out some of the fixtures so that you're using a lot less water.
Absolutely. Most rainwater harvesting systems in urban areas in Australia are retrofit, but we have a situation in Australia because of government policy that supports rainwater harvesting in cities where there are also many new installations. In the new ones are advising, the bigger diameter plumbing, probably the better within reason. Within the old systems, if you're just using the existing plumbing, and that's good. So assume small losses
for friction, typically. Right?
Friction losses. Be aware of the elevation head, which you've put up on the slide there, Michelle, because
that's the total dynamic head being this the amount of head pressure that your pump needs to supply, right? All the losses.
Yeah, say you've got this garden variety pump that will give you 30 meters or 100 feet of head, but throughout your plumbing system, because of bends and friction losses, you lose 90% of that, whatever that is. You lose 10% of that. You're down to 27 meters, if my maths is right. And if the highest supply point that you need to lift the water up to is 10 meters above it, you're probably going to be okay. So
right, so an example that would be a second story of your house, and your rainwater tank is at ground level, something like that, right?
Absolutely, and these are the things to consider. And I think you've got a little drafting design module that you've taken people through.
The elevation, looking at the elevation, and where the elevation I think becomes particularly poignant is underground tanks, buried tanks, right? Because then you're starting to have relatively possibly significant elevation head from the point where you're drawing water to where you might be delivering water.
Yeah, and it's very important to draw a little sketch of your house and when you're thinking about this problem. And so you've got the horizontal plan of the house and your rainwater harvesting system that is an important part of the sketching and thinking about it. But there needs to be a little vertical plan of, well, my pump is down here, and here's the highest point where it needs to supply water to. Now just be careful. So the highest point, the flow rate and pressure, which are, related to each other, that you require at the appliance is also a head. It's a pressure head. So you've got a pump that'll supply 30 meters ahead, 100 feet of head, and you've got, a friction loss of 3 meters, which is 10%. So you go, okay, I've got 27 meters of head.
Yeah.
And you say, oh, I'm okay because my toilet on the third floor of some building is, and whatever, is 27 meters above my pump. I'll be all right. Well, no, you won't, because there'll be zero flow rate and zero pressure by the time the water gets there.
Right, and that's the thing to understand, right? You still want some residual pressure head, but earlier you implied it's surprising it doesn't actually need to be possibly quite as high as the residential codes often recommend.
Well, if you're lifting the water, say that extreme example I just gave, if you're lifting the water up to a third floor and from down the bottom of a hill, which happens in a lot of country places in Australia, not the third floor, but from the bottom of the hill, and it's only a toilet at that level, a flow rate of 1 litre a minute will top up your toilet system. It'll just take a little longer. So, and
your shower might not be too pleasant though.
No, your shower might take a little while to get wet. But when you think about a toilet, you're not using it all day long. So you're not, you haven't got a big line of people outside of your door unless someone's got married at your house or something, or you've got you've gone out and your kids have had a party. So you don't have a queue of people at your door. They just keep flushing the toilet. So, when we did mapping of, the timeline of water use on any day in people's houses, there's plenty of time for the toilet system to fill up again, if the flow rate's a bit slower.
So what do you think of what do you think of a pump calculator like this one here, where you can actually it just help you figure out what this total pump head is?
This type of pump calculator is Pentair. I know these people.
Yeah.
It's actually quite useful. So say we said we need a maximum of 20 litres. So how many gallons is that?
Yeah, let's do that here. It's a quarter, right? So 20 litres would be 5 GPM.
Let's put 5 in.
Yeah.
Say a typical house, you're going to have about 100 feet of plumbing, unless your rainwater storage is a long way away.
Yeah, I think this is a little bit more common for indoor plumbing sizes. So
that's about the same as us, actually, 0.75 of an inch.
Okay.
And you need to lift it up at least 10 meters. What's that? 30 feet?
30 feet, yeah. That's a second level house, right?
Yeah.
Miscellaneous head losses. So this would be across, you could have 5 feet in your hot water heater and another 5 feet across your water filter. I did see a little, often manufacturers will list the head loss in terms of PSI. And so to convert PSI to feet, the multiplication, I believe, is 2.3. So multiply your PSI by 2.3 to get feet. And I'll say to the Canadians, maybe not so much the Americans, even though I really like to do all my calculations in metric, when it comes to pumps and tanks, you usually almost end up converting and doing a lot of your calculations in U.S. customary, because the suppliers pretty much only speak in U.S. customary, and it also depends a little bit on how old you are.
And so, Michelle,
Yeah.
Or if you want to use metric, there's a Pentair website in Australia that's in.
Oh, is there? There you
Yeah,
go.
yeah.
Use the Pentair, type Pentair Australia, and you'll have the metric
Um,
version of this. That's brilliant. But then you'll
so
still have to convert it to gallons per minute and feet when you talk to your supplier, probably. But
you
anyways,
will.
back to your
That'd
mislife.
be about 5 feet, wouldn't it, if you had filters and everything else?
Yeah, or maybe more. I'm not sure. I mean, if you
Yeah.
had a filter and a hot water heater, that's going to have a little bit of head loss. What other kind of things might have some miscellaneous head loss? If you had a UV system, if you decided you needed one, there'd be some head loss in that as well, right? Um,
Let's just try 5 for a moment.
okay,
I'm comfortable with 5.
okay, elbows.
So in a normal plumbing system, there'll be a number of 45-degree elbows,
A dozen.
um, and there'll be a handful of 90-degree elbows. Say 4. Oh, we've got 8.
Oops,
Yeah,
8. Well, sure, let's do 4. And then there'll be a
and there'll
few
be
of
certainly
these.
a couple of T's. Say 3.
Yeah, yeah.
Uh, and if you
And then I
hit
think update. There we go. The the pump head required, as per this calculator, is 42 feet or 18.2 psi. And this pump head includes what, elevation head, because we put that in over on this left hand side. It includes the friction losses. That's the based on the pipe length and the fittings. And there are some other losses that we put in there, but we did not put in the pressure head losses. Or I shouldn't say that. So we didn't put the pressure head, which is how much pressure we want from the fixtures at the supply point.
which is the same as the flow rate at the fixtures that's at the supply point.
So this number isn't quite good enough yet for us to size our pump. If we want to actually dive into looking at pump curves, we still need to add the pressure head.
Absolutely.
What we talked about previously is that although the residential code usually just says add 45 psi, it's a lot less than that for most rainwater harvesting applications. And then the next thing is, how do you figure out what that pressure head is? Peter, how do we figure out that pressure head? We know what the flow rate at the fixture is. We came up with 20 liters per minute. How do we convert that volume into pressure head?
So here, Michelle, you're going to make fluid mechanics, the dark art of fluid mechanics, take it out of Hogwarts and give us some simple rules for everyone else to use them.
I was waiting for you to pull out the Bernoulli equation.
Oh.
Don't want to scare students too much, but I think Peter and I talked about actually diving into this a little bit to just round it out and help give you an idea. And we're gonna dive into it, but I think we're gonna pull back afterwards and just help you understand that it's not nearly as intimidating as it might seem, and perhaps even necessary.
So, well, probably necessary, but if you know a few rules, you probably don't need to get down and dirty with water physics, which is the energy or Bernoulli equation. And Bernoulli was a smart fellow a few hundred years ago, came up with this idea. But Michelle's actually simplified this for everyone.
Yes, and instead of having you pull out your fluid mechanics textbook from university, I found a super nifty little calculator that I've embedded into the lesson below. Yeah, you need to know 5 things. You need to know the pressure at the pump, the height at the pump, and the speed of the water at the pump, which is tied to, of course, flow rate and the pipe diameter, as well as the height at your fixture and the speed of the water at your fixture, which is again tied to flow rate and pipe diameter. You input those into the calculator and it'll spit out the pressure required so that you can turn that into head for your curve. And let's just go through an example so it's less intimidating.
Well, to start off with, for fluid density, you can just put 1,000 in there. So
That's water.
Water.
Right.
Yep.
Yep. And then from the previous pump calculator, we determined that The pressure, the pump head pressure required was 18 psi. Something kind of cheaty about this calculator is you can actually mix your units. You can switch it. You can drop down and pick kPa depending on what units you're working in. But
good, I can work in language I understand then.
Yeah, it's really neat. But because we've kind of mashed this up a little bit, trying to use the North American, commonly manufactured used units, and then of course speak in metric as well. I apologize ahead of time that we're going to mash up our units a little bit.
This one's going to be 0.
0, because you can just use relative height, right? Now, speed. We need to convert the flow rate of 20 liters per minute into a speed. What I've done for myself to make this easier, and I'll share this in the materials tab, is a simple little table that correlates the flow rate in liters per minute and the various pipe diameter sizes along the top. And we know that your flow rate is simply equal to your speed times your area, or inversely, speed is equal to flow rate divided by area. And that's the calculation that's happened here. And all of these things are just to try and get the units converted to be consistent, so that we actually get the correct answer.
So 1.89.
Right here, yeah, we've got 20 liters per minute, and 1.89 meters per second would be with a pipe diameter of half an inch or 15 mils coming out of the pump, correct? Because we're looking at the speed of the water.
So we should make that pipe diameter a little bigger. So
yeah, would it be 50 mils, 2 inches?
It might be 1 inch.
You think it'd be this one?
Yeah.
0.68?
Yeah, for a classic system. So let's try 0.68.
Okay, let's try that. 0.68. And then the pipe diameter, we said that was
1 inch.
Yeah, I'm going to mash up my units again here. Now, position 2 would be the fixture position.
Yep.
We don't know the pressure. This is what we're trying to solve for. So you would input your height. So let's assume that we're really looking at the worst case scenario, which would be your highest fixture.
So
from the height of your pump.
So let's say you're 2 stories up, or your pump is at the bottom of the hill, 10 meters. Yeah.
Mm-hmm. And then we'll go back to that spreadsheet to look up the speed of the water, 20 liters per minute. And I think I'm going to use 3/4 inch, I'm going to assume plumbing, or 20 mil indoor plumbing. That's 1.06 is the speed. 0.06. And watch what happens when I input that speed. Our pressure is calculated by this little.
So your smallest garden variety pump, which is 30 kilopascals, is going to do it easily.
Yeah, so what we're saying is that the pressure head required at the fixture 10 meters up, where we're trying to supply 20 liters per minute, needs a pressure head of 25 kPa. So that's kind of fun to play with. And now we can go back. We now need to add that pressure head, though, to the losses we calculated from the calculator, because that's the elevation losses and the friction losses and the other losses that the pump's going to have to overcome. So I will take, let's do that, 27 kPa or 4 psi. We're going to convert that. You can do it in kPa, psi, or meters or feet. So it depends ultimately on which units you need for your pump curve. We'll get there in a minute.
9 feet or 2.7 meters.
So I've added I've added, oh man, and I'm struggling with this mashup of units as well. But let's do it in kPa, and then I'll translate it on the video for those in metric. But we've got our 27 kPa, which is 2.7 meters of head, and we can add the 2.7 meters of head to the 13 meters, which gives us 16 meters of head, or 51 feet of total dynamic head for our pump.
So,
was that clear as mud? Did that?
Well, it will give people confidence because the students can go through this step by step.
Mm-hmm.
This calculation for this situation shows that your normal 300 kPa or 30 meters head, 100 feet head, small rainwater pump is going to supply your situation quite easily.
Let's go look at a pump, just to pull up a pump curve and kind of illustrate that example. I am just simply, honestly, just Googled rainwater harvesting pumps and see what came up here, and
Gee, they're all big ones. So
this is quite big, but let's look at this anyways, because this will really, it is it's a rainwater harvesting pump, 1 horsepower, and if I scroll down here, you can see here's the curve, PSI versus gallons per minute, right? And we just calculated the gallons per minute was 5.2, correct?
Yeah,
right here.
You're right there.
Yeah, and the PSI is was like 4 plus 18, 22.
22. So you're right there.
Really low.
So that
right.
Now this is telling us something very important. This pump is too big for your application.
It's too big.
And there tends to be an overestimation in the pump market of what sort of pump is needed for rainwater harvesting. These ones are even bigger. So when it's saying 1 horsepower, that's far too big. But
let's check this one out here. It looks tiny bit smaller.
Same pump curve.
Same thing. Yeah, same pump curve. So we got to find something even smaller. Let's see, 1 horsepower. Here's the 3/4 horsepower.
Let's give that one a go.
Better.
It's out of stock, but let's have a look at it. So.
Yeah, well, at least it kind of gives you an idea of what. Now, where's the curve? I might have to open this up. Other details. Oh, here it is. I gotta click on it. Okay, so let's check out these units. Now, in this one, interestingly enough, they've got head in feet and PSI, and they've got flow rate in gallons per minute, and we could also do meters cubed per hour. But let's do the 5 GPM.
About there.
Which is right about there. And then going up. Same thing though. This looks 20.
About there, yeah. Closer to the y-axis a little bit. So about there. Yep.
Yeah, 50, right?
So what?
Yes.
What you're thinking about here is the you don't need a very big pump for that rainwater installation you were talking about. Like this pump will do the job. It'll just be oversized, but this will help people because manufacturers tend to point rainwater harvesters to very big pumps, and that can be counterproductive. However, we've now given people a tool to find a pump that suits them. Don't choose one that's too small, obviously. So if one is slightly larger than you need, which it's likely to be, that will be okay. So
yeah, exactly. All right. So, what do you say, Peter? How important is for designers in every situation to go through this level of detail that we did in terms of thinking through the flow rate at the fixture and calculating the pressure head and then adding that to your pump head to come up with your total dynamic head and then looking at a pump curve to see how it matches?
There's 2 answers to this. If it's just someone wanting to put a pump in their household, it's to know about this is vitally important, so it avoids the homeowner or the designer getting this quite wrong. Don't accept someone making an argument to you if you get it too big, it doesn't matter because it's conservative, because you'll find that'll create massively counterproductive outcomes. You want a pump that's close to what you need. Dramatically oversized is not a good design, even though there are many hydraulic engineers who will tell you it's conservative, it's okay. So going through this lesson, which we've just done, this one and the one before, and having an idea what this means helps you get your choice in the ballpark, or it allows you to ask the right questions of whomever's supplying you the pump. Being able to actually go through it and calculate it yourself with certainty is probably an ideal outcome, especially if you're going to design more than your own home rainwater harvesting system.
But I think you'll get a sense pretty quickly if you start doing a lot of home scale rainwater harvesting designs. You know, if you're a practitioner who's actually doing this professionally, you'll probably find that there's one pump that fits 90% of the applications that you're looking at.
And this is what I've found. I've designed thousands of them. We only choose a different pump or different configuration for a pump if the site is unusual, if there's a big hill, or it's a 4-story house, or something quite different. You normally end up with something that works for you and a feel for how the numbers work. So if you go through this 1 or 2 times, you know what the answers are going to be most of the time. Not that we want people grappling with pump curves, but they are quite useful once you understand them.
We live in a city where there's quite a substantial oil and gas industry and quite a large pump industry of really good, reputable suppliers. So I'll be perfectly honest, I've always found that picking up the phone and finding a good, reliable supplier is incredibly insightful. And you definitely want somebody that you want to be able to ask good questions, and you want to really explain your situation. But I do think you should be able to find people that can be really helpful and genuinely interested in helping you find the right product for your particular situation. And so you don't need to be a pro in pumps at all.
No, but if you know your basic parameters, which we've discussed in this lesson, it really helps the pump manufacturer assist you in the best way they can.
Yeah, you're right. And I guess watching out for the possible and maybe potential scenario of them just saying, oh, it's okay if it's 2 times bigger than you need it to be. It'll just work better. Right.
Not always.